We are going to now learn different signal conditioning circuits for capacitive sensors. We learned that a capacitive sensor, we can change the distance between the plates. If this is the capacitive sensor where area is A and one plate moves by small distance x, then we can write the capacitance C equal to epsilon naught epsilon r A by d plus or minus x. So this we can rewrite it as epsilon naught epsilon r A divided by d into 1 by 1 plus or minus x by d. So this we put it as C naught. So this will be C naught by 1 plus or minus kx, where k is 1 by d. This can be written as C naught into 1 minus or plus kx if k is much less than 1. Normally we do that anyway. So one of the very famous capacitive sensor I have already taught you is the electret microphone or condenser microphone. Right? Now if I have one capacitive sensor that varies, then I can simply connect the capacitance in series with the resistance, excite by a DC voltage, and get the output voltage V0. So for derivation, what we do is this: we get C0 plus C1 sine omega t, assuming that I am now sending only a single frequency sine wave excitation to the microphone, right? Maybe a flute. So the thing is, this we call it as battery voltage EB. The voltage V0 is I times R, where R is the resistance and I is the current. And if this is voltage is the capacitor, then I have Q equal to C0 plus C1 sine omega t into Vc is the voltage. I is equal to dq by dt, which is C0 plus C1 sine omega t into dVc by dt plus Vc into omega C1 cos omega t. Right? This is variable separable differentiation. We do that, then V0 is equal to C0 plus C1 sine omega t into dVc by dt plus into R plus Vc into omega RC1 cos omega t. Now this is a nonlinear differential equation. Little bit difficult to solve. So since we are giving input as sine omega t, we assume that the output could be sine omega t or cos omega t. So we can generally say V0 is A sine omega t plus B cos omega t. So now I can write it as A sine omega t plus B cos omega t equal to R into C0 plus C1 sine omega t into d by dt of EB minus, because Vc is EB minus V0, right? V0 we already know, A sine omega t plus B cos omega t. So this will be A omega cos omega t plus B omega sine omega t plus Vc, again we write it as EB minus uh, A sine omega t plus B cos omega t, right? So solving this, we can get A and B. Uh, I am not going to solve this, it's not really necessary. Those interested can solve. But here again, if I see that this would become cos omega t, sin omega t, or sin square omega t, all would be there. The one way we can reduce the non-linearity is that make C naught much greater than C1. If you do that, obviously the non-linearity reduces. So what we normally do is, when we make the capacitor, we put for D a dielectric constant epsilon r, and X is of course either in a fluid or in a air with less epsilon r. So this way we can make C naught to be quite large compared to C1. So most of the electric condenser microphone, if you take, you will see that the backplate is filled with a dielectric which has a constant anywhere between 100 to 1000 depending upon the material used. So this is one particular type of this thing. So most probably, if you buy a electric condenser microphone, the microphone is will have three terminals. Uh, so this is plus VCC output, ground. This is the capacitor microphone. So the FET is automatically introduced, already introduced inside the package. So you get this. You can Google search condenser microphone circuits. You can easily see that. Uh, the reason that we use a FET is here, if you make the resistance large enough, then the capacitance impedance will be small compared to the resistance, and the nonlinearity is introduced by the capacitance, and that would be very small. So that is also one reason why the resistance is made. The other uh, uh, is when we have differential capacitive sensors. C1, C2, where C1 is equal to C naught into 1 plus or minus Kx, C2 is equal to 1 C naught into 1 minus or plus Kx, or is equal to C naught into 1 by 1 plus or minus Kx. I will put this as minus or plus Kx. C2 is equal to C naught into 1 by 1 plus or minus Kx. Again, this is wrong. Minus or plus Kx. So once again, if I can simply put this as R and R, you can get V naught in terms of EB. Again, that I leave it to you as a homework. Please find out V naught in terms of Kx. It's quite simple, you can derive, right? One form of bridge that is quite popular, which we already saw in the is called the Bloom Lane bridge, which was quite popular for differential capacitive sensors for signal conditioning. But as I already told you when I talked about the inductive sensors, This is not very popular. One Another circuit is that we have C naught into 1 plus or minus um, CF, and of course we need this circuit to be stable, we need an RF. So this is another circuit for single capacitive sensors. Now if I have a circuit right. This circuit will oscillator is an oscillator, so it's called the relaxation oscillator. Let's assume that the position is 1 uh, and the output is 1. So I write it here. So output is 1, and this is VC, it is 1, and this is I call this as integrator output, VI, V0I, output of the integrator. Now if this is connected VR, there will be a current VR by R in this direction. That current has to go here, and that current will increase the voltage like this. So this is VR by RC into T. So once it reaches plus VR, right, when it reaches plus VR, when it goes below that, it will go to 0. Am I right? Oh, this has to be uh, minus plus. I'm sorry. So it will change the moment it reaches it, this will change, and so then it will start going down. So this will go to minus VR. This is 0. This will, when it goes to minus VR, this will again change state. So I will have, so this is minus VR, this will be plus VR. So the thing is, the charge here is 2VR is the thing, VR by RC, right? So that is 2RC. So this time would be 2RC. This time will be 2RC. So I'll have total time T equal to 1 by 4RC, right? So the oscillator will work. Now we use the same oscillator. What we do is we now put the capacitors, right? Um, we put this is ground, this is ground, and I think I'll have to redraw this completely, right? So either this is connected to the input or ground. Again, this is connected to input or ground, right? So this, again, when this is connected to input, this is connected to ground, and so this controls. So I have switch S2, S3. There are three switches now. No, this is S1, S2, S3, and S4. Four switches. Now this is C1 and this is C2. So when it is 1, so this will be 1, this is also 1, this is 0, this is 0. So only C1 is connected. So the on time would be VR by RC1. When it changes over, when the okay, when it changes over, now C2 is connected to ground, C1 is connected to ground, and C2 is connected to the input, and hence we have, this would be VR by RC2. Again, 2VR by RC1 would be T on, and 2VR by VR by RC1, R into C2 would be equal to T off, right? So we take this and put an integrator, get the output. So I will get V naught would be 1 by T integral 0 to T, whatever we switch dt. So this is 1 by T integral 0 to T on, it would be 2 VR by RC1 into T, minus T on to T, because this is on time plus 1, this is minus 1, minus VR, 2 VR by RC2 into T, right? So this would be will be T on minus this is 2 here, there is no 2, right? T on minus T off by T on plus T off into VR. So that would be equal to, if I substitute this would be case C1 minus C2 by C1 plus C2 into VR. So the output of the integrator, even though we say integrator, we simply put a low pass filter with the cutoff frequency much less than the oscillator frequency. So we get V naught, this we have already evaluated, would be kx, right? So we can put it kx into VR. This is C naught into 1 plus or minus kx minus C naught into 1 minus or plus kx divided by C naught into 1 plus or minus kx plus C naught into 1 minus or plus kx. So C naught, C naught, C naught, C naught cancels out. 1 minus 1 cancels out. So this plus or minus kx, plus or minus 2kx. Here plus or minus kx minus or plus kx cancels out by 2 into Vr, that is kx into Vr. So that's what we will get. So by using a simple relaxation oscillator, a differential capacitive sensor can be easily um, uh, converted into voltage, where the voltage is proportional to the displacement being sensed by the capacitive sensor. Again, it doesn't matter if I put the uh, C naught as C1 by 1 minus or plus kx minus C naught by 1 plus or minus kx divided by C naught by 1 minus or plus kx plus C naught by 1 plus or minus kx. This is inverse relationship. Again, C naught, C naught, C naught cancels out. So this I can get 1 minus or plus kx into 1 plus or minus kx. Here again, 1 minus or plus kx into 1 plus or minus kx. So I will get 1. Okay, now we get here 1 plus or minus kx plus 1 minus or plus kx. So this cancels out, this cancels out. This will be plus or minus kx plus or minus kx plus 1 minus 1 cancels out. This again kx into Vr. So I have whether linear relationship or inverse relationship, I get the same um, output. So with this relaxation oscillator circuit, we can get an output, analog output, which is proportional to the displacement being sensed by the capacitive sensor. Thank you. Yeah, in the analog output signal conditioning circuits, we saw a relaxation oscillator type signal conditioning circuit where the output is proportional to C1 minus C2 by C1 plus C2, and hence it gives a linear output whether we change the area in the capacitive sensor or the displacement between the plates in the capacitive sensor, which means the output is linear, whether I have linear characteristics for the capacitive sensors or inverse characteristics for the capacitive sensors. That circuit has some small problems. Number one, none of the terminals of the sensors are at ground potential. Um, they are one terminal is at virtual ground potential, but the other terminal is at supply voltage. So any uh, sensor capacitance change due to parasitic capacitance would affect, and also the parasitic capacitance comes as a load on the operational amplifier, which is not very good. So we can slightly modify the same relaxation oscillator circuit so that we can obtain the similar characteristics. Here what we do is we take the capacitive sensors, whether linear characteristics or inverse characteristics, and we put them under the switching scheme. If you look at this circuit, you see that the sensor capacitor C1 and C2 are coming at the input and get switched between the two voltages plus VR and minus VR, and the output of the second switch is given to the inverting input of OA and of course OC. Again, there is a feedback. This is basically a relaxation oscillator circuit. So let's see how it works. So when we do this switching, you see that the output increases continuously. Once it touches VR, the comparator changes state, and what we have now is this particular condition. So once again the switching continues to happen, and we do this till it goes to minus VR, and when it reaches minus VR, the comparator again toggles, and we get continuous oscillation. So if I look at this, this will be the circuit. Uh, we have an on period where comparator is 1, off period where comparator is 0. So if we look at the output of the low pass filter, which is the average value of the this pulse train, um, so we calculate this to be T on minus T off by T on plus T off, the same as the previous this one. Of course, we know T on is T2C by C2 in whatever into the switching frequency, and T off is again 2C by C1 into switching frequency. So we put this in T on minus T off here. We get C1 minus C2 by C2 plus C1, so which becomes VR into K into X. VR is the reference voltage that we switched in, K is the transformation constant of the sensor, and this is true for whether the characteristics is linear or inverse. So this circuit also is a relaxation oscillator circuit, but it has a lot of advantages. If we have integrator capacitance C, if we increase or decrease, what happens is that the relative error is affected as given here. If you have reference voltage increase or decrease, that again directly increases the right. If you have switch resistance, of course we can combat the switch resistance by simply adjusting the clock circuit so that charging and discharging occurs within one clock cycle, so we can make it completely irrelevant. The comparator delay gives very small errors in the output, 0.002%. Op-amp bias current again has absolutely no effect. Stray capacitances, where if they are present, have again no effect. So this again was put in right. A novel switched capacitor relaxation based circuit for differential capacitor sensors have been presented here. The circuit gives a linear output for sensors possessing linear as well as inverse characteristics. Effects on all important parameters of the performance circuit is analyzed, and it's not that big a deal. Since the output is low pass filtered output, um, it automatically eliminate high frequency noise. Also, it is easy to interface to a digital circuit. Worst case error, as I said, is very small. Thank you.